problem to solve. That is an interaction which connects initial and final channel. That's an interaction within the P space. So I call this the V beta alpha. V beta alpha or alpha beta, that is an interaction which acts in P space. So that is now part of our Hamiltonian. Yesterday we defined an interaction VPQ, which was connecting P and Q space. Now we are, so to say, boiling down the problem to a coupling to define more details in the P space. And then I'm having here those nuclear matrix elements, and I have another channel of that type, and correspondingly K beta plus U beta of R alpha R beta minus E beta chi beta plus the conjugate of that matrix element V beta alpha AA chi alpha plus equals 0. So that's now the problem which we are going to consider. Sorry?
In the TWBA case, the upper right term, the V alpha beta between AA and BV, will be neglected.
Oh, that is, this is assumed to be purely non-diagonal. All diagonal interactions are included here in this optical potential. Yeah?
So it can be completely neglected here.
It's not neglected, it's included in the optical potential. In the formalism, we don't have to take that into account, yes. Yeah? So there is also, let's say, there's V alpha alpha, V beta beta, and they are contained in these optical potentials. We are only concerned about these non-diagonal channel coupling interactions in the moment. But you were right. I mean, they are present. They are part of this projected effective Hamiltonian. And so they are contained partly in this non-dispersive part, VPP, and partly in this VQP part, or better to say in these induced self-energy parts. Yeah? But here we assume those parts are given. This Hamiltonian, the effective channel Hamiltonians are in these two pieces included. Let's see, do we have some chalk? So those pieces here, these are these effective Hamiltonians now specified or boiled down to the channels alpha and beta. Okay. So, and these, you see, these are nuclear matrix elements involving the overlap of initial and final states of the nuclear intrinsic configurations, folded or taken an expectation or a matrix element, it's not an expectation value, but a non-diagonal matrix element with this interaction V. And these matrix elements in reaction theory, they are called the nuclear form factors. So that means we can define those objects as nuclear form factors. And so that is then F alpha beta, that is A alpha beta, B and B. And we come later on to study those in more detail. And with that I get a slightly more condensed or elegant formulation. So I can now introduce again as before our effective Hamiltonian. And here distorted waves. And then I'm having this form factor V alpha beta, chi beta plus equals to 0. And here I'm having H beta effective minus E beta chi beta plus F alpha beta. That is, if you look very carefully, that is essentially the Hermitian conjugate of that operator. So, but we can keep that notation F beta alpha alpha beta chi alpha plus equal 0. So as it stands here, that is a 2 by 2 coupled channel problem, right? So I could solve it as a coupled channel problem. I can even take more of this type of equations, and then I add more pieces in each of those lines, and I add more lines of the same structure. And in practice, one may include 10 states or so out of these 10 to the 6 per MeV, which we discussed yesterday. But what is the observation? The observation is that the elastic scattering produced by this effective Hamiltonians here, that is by far the dominant one. That is, say, for a proton on a medium heavy target like tin, it's about 1 barn, the total cross-section which you derive there. These inelastic processes, as a single process by themselves, they account for, say, 10 millibarn. A millibarn is 1/1000th of a barn. So that is 1%. 10 millibarn is 1% of the elastic cross-section. So that means there's good reason to believe that in most cases I'm doing well to solve that perturbatively, that problem. And I do this under the constraint by including to all orders elastic scattering effects. That is called initial and final state interactions. Initial state interaction, that is the elastic scattering of the incoming channel in the incoming channel, A plus A or alpha, and final state interaction are all elastic scatterings in the outgoing channel. And so that I'm making now perturbation theory with already distorted waves. And I do it in first order. First order perturbation theory is typically called the Born term, but it's a kind of deceiving because I include to all orders elastic potentials. So that means the major effect on the wave function, or better to say, on the scattering amplitude, is included. And then I'm allowed, for this 1 barn effect hidden here, I'm allowed to say this 1 millibarn effects coming from those non-diagonal pieces, I'm allowed to add perturbatively. And that gives us then the definition of the distorted wave scattering amplitude. And that is, say, for the moment I take this index, upper index DWA, just to remind us, but I will leave that out later. And that is defined by having here the incoming solution of that second equation here, the form factor connecting beta and alpha, so that is here the driving term of the channel coupling, and the incoming channel wave with outgoing boundary conditions. You might wonder why is here these chi minus appearing. That is actually There's a big discussion if you look in the literature, in particular in the 60s, when one tried to understand the structure of those equations here. People were oscillating between this chi minus beta and chi plus beta. The answer was already given by Mott and Massey in the 30s. They showed that if I have these expressions like this, they are coming actually from this S matrix definition, that the S matrix is defined like this. And if you boil this down to a scattering amplitude, then you find that if you replace now these full channel states by the distorted waves, that you have structures like this. So that is very important to remember, that one really needs to have here this incoming plane, this incoming distorted wave. These incoming distorted waves, they are related to the outgoing distorted waves in a simple way. Chi minus dagger alpha of k alpha r alpha, they are simply chi plus alpha minus chi alpha and r alpha. So that means they have a simple conjugate complex or Hermitian conjugate related to the complementary distorted wave. And you see that this chi minus dagger or complex conjugate is the solution of the same type of wave equation than the chi plus would be. Yeah. You can extend that if you look into the literature, if there are spins, then there is also a spin-dependent phase involved, but these are fine details, and we are not concerned with those fine details. What is behind this relation, which is one of the fundamental relations of scattering theory, is that these are incoming and outgoing spherical waves are related by time reversal. That is what is expressed. Because as you see, there is a sign in the momentum direction. Yeah? The one is outgoing, the other one is incoming. And that is just expressed. So that means what is behind here is a kind of a time reversal symmetry or transformation, not symmetry. And that is because these k alpha goes over to minus k alpha. And these spin-dependent phases which I was mentioning, they are related to redirecting the z components of spin during this time reversal. Okay, so that is our working tool. Oops, that is not very good. Take this one. And those equations of that type are essential for the next 3 or 4 lectures and these applications which I'm going to discuss in a moment. Okay, so now we can also define the DWA cross-section just for completeness. To now we mainly have been concerned with elastic scattering. Now we are going to non-elastic processes, and therefore we look at the action in terms of those scattering amplitudes, and the sigma d omega, that means the angular distribution in all glory, is given by the effective masses in the incident and the exit channel divided by some phase space element. Then there is the again part of the phase space, the channel momenta. Then if the projectile and target typically have their own spin, and I have to average over all initial spins of the projectile, all initial spins of the target, And that is the case for unpolarized cross-section. That I mean I'm not observing spin polarization. And then I have to sum over all projection and the final state. And that I have to evaluate, so this amplitude in all those details. And for the moment, I'm again adding this index DWBA in order to remind us that this type of amplitude, what I'm talking about, okay, take here a capital 1 because that is MA, MB. So then it's MA, MA going to MB, MB. And the whole thing depends obviously on K alpha and K beta, the channel momenta and their directions. And well, actually, I can now extend that cross-section to a multidimensional cross-section or multi-differential cross-section, namely that one which is leading to excited states in the projectile and the target. And therefore, I have to add to sum over all these wait a moment, projectile and the target. Then I have an energy distribution per MeV in the final nucleus of the target-like object. And I have an energy distribution in the projectile object. And that is by, I have to split up the total energy transfer E in an energy conserving manner. That means what I put into excitations of the one nucleus, I lose for excitations in the other nucleus. And E is the total energy transfer, and so that is then taken into account here. If you add these two arguments, then you see they add up to the total energy transfer E. So you had a question.
Reduced mass for the beta system should be under a denominator, really, because the cross-section is proportional to the ratio of the outgoing speed and the incoming speed.
Yes. The outgoing spin is taken into account by those summations. Speed. Ah, the speed. Yeah, okay. That is taken into account here by those ratios. That is momentum. Multiply that by h bar. Then you have p alpha and k alpha. And that is essentially the ratio of velocities. Yeah? And if you work out, now see what I'm using. I'm not using the scattering amplitude, but the T matrix. Yeah? And so if you remember what we said the other day, there is a prefactor, and that is taken into account and leading finally to this modified total prefactor. Yeah?
What is this?
Sorry? E prime, that is the excitation energy in the B system. Yeah, and that here, that in total is the excitation energy in the projectile system. And you see, I mean, now I can integrate over one of those systems. Suppose now that, say, the projectile does not have excited states like the proton, at least not for our interest. There is no excited state of the proton. Then this would be a delta function. Then you can integrate easily over the target projectile energy distribution and then obtain a double differential cross-section which only takes care of the excitations in the target. And if I have a discrete spectrum in projectile and target, you remember maybe from our first lecture that at the beginning of the spectrum you had these spikes separated very well. And then these S of E's, they are given simply by delta distribution of delta functions, which have spikes at the excitation energies. So that is here our energy axis. Here they have the first excited state, they have the second excited state, they have the third excited state, and so on. And you see, if at a given total energy or available energy, I'm hitting the one or the other. And if I vary the energy, like in the spectral distribution, which I have shown you, then I'm scanning through those structures. If I'm going above particle threshold, for example, then these delta functions become Lorentzian distributions or Gaussian distributions. And then they are overlapping and smeared out, and they also become Lorentzians if I take into account that, say, a single configuration is coupled to many other configurations. Like Simonel has discussed that in this TD-HF or TD-RPA, and I think Baraka is also discussing that probably in these damping effects. Then these delta functions become Lorentzian distributions, and the spikes are becoming then overlapping distributions like this. Okay. The higher I go in energy, the broader the state is, so the more flat the spectrum becomes. So that means we have here now available a toolbox which allows us to calculate all types of reactions of interest, and I can easily then obtain the double differential cross-section dE d sigma, that is by integrating, say, over EB prime or EB d3 sigma dE B d omega. I can get out the angular distribution, the total angular distribution, by integrating the double differential cross-section again over energy. And I get out the total cross-section for this particular. I should always add alpha beta, right? Because we are considering a particular channel, not the total result. And that is d omega, d sigma, alpha beta, d omega. So that are important observables, and they have their own characteristics and their own type of information. The most detailed information is certainly in this triple differential cross-section, because there I see the structure, the spectral structures, in addition to the momentum distribution of the transitions for projectile and target. Here in this case, I'm seeing essentially the spectral structure and the momentum distribution of the target, say. And, well, here, in this case, I'm seeing the momentum structure of the whole reaction, and this one here is the total yield. And so that means one gets a lot of information out of those different types of cross-section. Okay, now since we have defined the tools by which we can study now reactions, we do so. And I mentioned at the very beginning of our lecture series that the discovery of direct reaction was related to data gained by dP, by transfer reactions, and PD, the complementary one. So, and since these type of transfer reactions are still a very important way to study reaction theory, but also to gain spectroscopic information out of nuclei, I will start to discuss that first. And So what is what? So transfer reactions, that's our next topic. That is now in the new sequence, chapter 6. And we agree everything is done in DWA approximation. So what is a transfer reaction? I'm coming in, again, that is a general scheme. Now I assume that, okay, let me have a slightly different A prime and A prime. So let's assume that we can also, let's keep it like this. So now we assume that A has a substructure, namely is given by a core nucleus B or the core nucleus B and a particle X, and B is given by the initial nucleus A plus X. So that means if I'm looking in more resolved detail, so to say, to this reaction, then I'm describing a process which is of this structure. X can be a neutron, a proton, a deuteron, an alpha particle, or say also mass-3 systems, helium-3, a triton, an alpha particle, whatsoever. So for all those possible combinations, you will find studies of experimental and theoretical kind for these transfer reactions. We consider in particular this one here. Namely, and we consider that A equals D. So that means we are considering this process, and that is called a DP reaction. And the notation is then, which you find also on my transparencies and in the lecture notes, that one denotes those reactions as A, DP, B. So it means within the brackets there is the projectile sector denoted, and outside of the brackets you have the target-like one. And projectile means that the first one is the incoming, and that is the observed particle. Sometimes you can certainly also look for recalling particles, and you make it a different way. Anyway, so what is then the problem with those reactions? Well, if you look carefully, then you see there's a rearrangement not only of mass, but there's also a rearrangement of coordinates, because the center of mass is changing. And that is denoted here for such a DP reaction, or better to say, I mean, this is still quite general, as you see from this plot here. Yeah, so that is the initial system A, that is the final target-like system B, in which the so X is taken away from the A system and attached to the B system, and then the initial channel coordinate for relative motion is between the center of mass of A and the target nucleus capital A. And in the final channel, we have a different situation. Namely, the channel coordinate R beta is given as a relative coordinate between the remaining projectile-like residue B and the newly created target-like capital B. And that has to be taken into account. And that means, so the natural coordinates in that respect here are certainly those coordinates which are describing the motion or the states within the projectile and within the target. But for the description of the reaction, I need to have those channel coordinates. And you see, I mean, it's a simple geometrical problem to relate the one and the others. And I'm not going, I'm leaving it to you to evaluate this transformation. It's a linear transformation given by mesh ratios, and the what one finds is, or the best way to approach that is to express natural coordinates, namely those ones acting in the projectile and the target, and that is the initial one, that is the final one, and I can simply write S1 R alpha plus T1 R beta, and S2 R alpha plus T2 R beta. And I leave it to you to get down those transformation coefficients. So they are given in terms of the A's and capital A's and B's and X's, and so I mean, these are these three independent coordinates, and correspondingly the T's. So that is what we need to have. And you see, if I make a coordinate transformation, then I always have a Jacobian. And this Jacobian is given by the by these expansion coefficients here. Yeah. So the Jacobian J alpha beta, that is, so to say, given by dRi with respect to the d alpha beta, let's call it 1, 2 to 1 beta, in the symbolic notation, it's a matrix, or better to say, a determinant of a matrix. And that is S1, T2, S2, T1, essentially. And so then we have to think about what's about the Hamiltonian. So I have an Hamiltonian H alpha. I leave out this effective because we agree that we always have that. That is the relative motion hammer, the kinetic energy operator in the initial channel, the optical potential in the initial channel, then Hamiltonians in the initial channel, and one has some interaction acting between projectile and target in the initial channel. So this is an interaction VAA. That means all those pieces which are not covered by the first part I have put in the second part. So what could it be? This is only good for elastic scattering. There might be now contributions from breakup of the deuteron, from inelastic excitations and all those things, so they are supposed to be. And there's also the final state interaction, and with its own optical potential, and with different intrinsic Hamiltonians, and with residual action of that type. And since the total energy is conserved, both must be the same, right? Just by the conservation of the total energy. And now I can use the one or the other. As long as I do everything correct, it doesn't matter. But in order to keep trace about those interactions, it's these V's appearing there, and also here these differences in optical potentials. The one or the other representation might be good, might be easier to handle. Good in the sense it's easier to handle. If you look into the literature, then you find extended discussions whether to use this one or this one. That is called the prior representation, that is called the post representation. And for the DP reactions, it is of advantage to use the post representation also of the wave function, and because, as we will see, that leads to rather simple expressions. There are other complications. So since the change of coordinates, all those things here are no longer, also the channel wave function are no longer orthogonal, because a plane wave with an argument R alpha is certainly not orthogonal to a plane wave with the argument R beta, because there is some recoil correction from the one to the other. Also that we don't discuss. It's not important, better to say it can be taken into account properly in certain approximation for this DP reaction. These non-orthogonality problems, they become more important if you have a transfer induced by heavy ions. You should ask Jose Antonio Ley. He's a specialist on those things. He is struggling always with those non-orthogonality terms and other complications. So for DP reactions. Now we have to look what is then this. So we have defined, so to say, our initial and final state problem. Now we have to connect initial and final state. And how is that done in a transfer reaction? Well, that is a one-body operator acting in the one nucleus and a one-body operator, single particle operator acting in one nucleus and a single particle operator acting in the other nucleus, because I'm annihilating a nucleon in the projectile and I'm creating a nucleon in the target. And that means this transfer operator, which I can assign to the process, that is, say, given by this expression. Let's call it A, B. Namely, if I use second quantization language, that is a particle operator creating a particle in the AX system and annihilating a particle in the BX system, in the initial system. So, and that here I've used a field operator or a state operator language. So these psi beta dagger that I can now compose in terms of wave functions with energy levels n and angular momenta j and m, and that is then RAX. And so that is our R2, by the way, on this notation there. And then I'm creating a nucleon by acting on the ground state of A. So I attach an additional nucleon, and that means my system B is then obtained by acting with this operator on the system A. And then I can describe the effect by taking the overlap. So that is then A psi dagger B acting on A, and you see that is kind of an expectation. Sorry, B. It's a transition matrix element, and that is then now depending on the spectroscopy of the system B, which type of those wave functions is really being selected, and everything is coming down to the evaluation of this second quantized matrix element. Now I have to invent a model for the state B. And the simplest case is what one might call the Hartree-Fock choice, namely a single particle picture. Then I'm saying B is given by some K, J prime, M prime acting on A in second quantization. That is a simple. I can also extend that to pairing. Then it's a quasi-particle operator, not a particle operator. And then I can evaluate this, right? Then I'm simply having here to evaluate an object. That one, by the way, is called the spectroscopic amplitude. And this spectroscopic amplitude in this simple one-body description or single nucleon description of the final state, that is then of this type. Well, and then how do I deal with this? We know these are fermion operators. And if I have the anti-commutator of two fermion operators, they give a delta ij. And so that means I can replace this here by, or exchange that through the acting with this annihilator on the initial state, and by definition the acting of the annihilator on the initial state, that is then given 0. Yeah. So that means this spectroscopic amplitude I can now write like this. Under the constraint that A and Jm acting on A is by definition 0. Because that state is not occupied in A, or it is occupied, then I cannot act a second time with it, on it. So, and this one here, as you see immediately, that gives delta nn prime, so diagonal in the energy state. And it's also diagonal in the momentum, in the angular momentum, and the projection of the angular momentum. And that means our this Hartree-Fock approximation, our spectroscopic amplitude, or the matrix element there, the total spectroscopic amplitude, lack of space, that becomes in Hartree-Fock simply a wave function Jm prime of R2 Rax times the spectroscopic amplitude. And the spectroscopic amplitude in our case is simply unity. But we can keep that in a more, for later use or for general use, by introducing a new object, the so-called coefficient of fractional parentage. And this coefficient of fractional parentage that has its own notation, that is, in our case, let's call it here without the prime. That is then JAJ, so denoting the initial system, denoting the added angular momentum. And then there's a curly bracket And one is having here the final system. And that is called the CFP, coefficient of fractional parentage, which in the Hartree-Fock approach is unity. But you can certainly make more complicated models for the nuclear B. So it's not only a single particle state, but there's also a two particle, one whole state, a three particle, one whole state. There are one particle, two particle, two whole states maybe, and so on. Yeah.
So why are you looking at this matrix element in the first place, with the B psi B plus A?
I need to implement this nucleon into the A system. So I have to find out by which probability I do it in a certain level.
Okay, so
Yeah.
you're looking at the overlap of B with adding B to A?
Right.
And
Yeah.
that tells you about this spectroscopy.
Right. And if you look to the literature, this notation that comes from is in use for shell model description, so the interacting shell model description. So that were there where you take into account many body configurations and mixtures of many body configurations in this state vector of B. And then this is a non-trivial number. So, but you see, what we need for a single particle transfer reaction is the coefficient of fractional parentage for a single nucleon. And if that function is made up of many body configurations, then the single nucleon component has only a fraction of unity. And that is the idea or the meaning of this fractional parentage. Yeah, so that might come down to 1%, or it might be 90%. Then it's a good single particle state. And that depends very much on the spectroscopy of your nucleus. So the same thing can certainly be done also in the projectile-like sector. And that means our total form factor, alpha beta, which is now an object either of R1, R2, or it's an object by our coordinate transformation of R alpha, R beta, and that is then obviously given by psi A evaluated between in the projectile system, and then what we did here explicitly, evaluating the creation operator in the target system. So that is an annihilation, that is a creation. Yes?
A couple of questions. What if we have not only one nucleon transfer instead of this one?
Then you have to enlarge these operators. Two nucleons, it's an A dagger in the one system and AA in the other system. Or you alpha particle that you would treat as in the first place as an object by itself, as a entity. Then you would have to have an alpha particle creation operator and an alpha particle annihilation operator. Good question. That is a very good question. The cluster structure of nuclei would get involved. And that is an own field of research. So if you look into the literature, then you find a lot of books on cluster structures in nuclei. They are alpha particles. They are most pronounced or found, better to say, in N or in A equal 4N nuclei, up to calcium-40. So that means it's beryllium 8. That is the model system for alpha particles. It's unbound. It's two alpha particles forming a resonance if you add a third alpha particle, then you are coming to carbon 12, and that is most prominent seen in the so-called Hoyle state, which is one of the key states for nuclear synthesis. Without that 0 plus state at 7.6 MeV in carbon 12, which has this very distinct pronounced alpha particle structure, you would not exist, because that is the key state for producing heavier elements than mass 8 elements, and so on. There are other states in oxygen 16, again a 0 plus state, where 4 alpha particles, or the decay in 4 alpha particles is found, and so on, up to calcium 40. And certainly also in the very heavy elements, they decay by alpha particle emission. And there you see that this is, yeah. That's the same, except of angular momentum coupling, which I don't discuss here. Yeah, so the coefficients of fractional parentage, that is the, do you know, who knows about Wigner-Eckert theorem? At least there are a few, and you are in particular yourself. Good. Then a matrix element including M dependencies, the magnetic quantum numbers, can always be decomposed in a Clebsch-Gordon coefficient and a reduced matrix element. This one here, that is carrying the full structure of angular momenta. The CFP is the reduced matrix element. And so it's a simple number, not depending on magnetic orientations of the spins of the final and initial nuclei. So, yeah, okay. Anyway, that would have been the next thing to write down, namely, now to evaluate this one here, and that comes then down to a structure which is leading to a T matrix element, which is in the, so we are using the so-called post representation without going into the detailed discussion of it. I'm only giving you the result. The total form factor F alpha beta. Okay, here I haven't yet, I forgot something, namely there is an interaction between B and X which has to be included. And therefore this total form factor then can be written as UBX of RBX. So that is the post representation, and the strange thing is in the post representation you get out the initial, the prior interaction between the transferred particle and the projectile-like core. So, and then you have these wave functions. I call them NA and NB without going for the angular momentum now. And then it's NA dagger von RBX, and then it's phi NA of RBRAX, and then I can add these two spectroscopic amplitudes. Well, that is a particle-like amplitude connecting B, A, and X. So it's essentially, yeah, okay, at that level we still would have to, okay, let's use this condensed notation. And then you have a whole type spectroscopic amplitude, which is connecting B and A by the transfer of X. And these spectroscopic amplitudes, say B, A, X, they can be decomposed according to the Wigner-Eckert theorem. And let's take this one here as an example. And then you have reduced matrix element that is denoted like that. And that is the CFP, this reduced matrix element. And I can do the same thing certainly for the target, for the projectile like amplitude. And that is a Clebsch-Gordon coefficient. And the whole expression, this reduction, is called the Wigner-Eckert theorem. Okay. So let's write down the T matrix element, then we have a short break. So this T matrix element, that depends on K alpha, K beta. And now I'll write it down in, there's this Jacobian, dr alpha, dr beta, and then I'm having my final distorted wave. Here I'm having this form factor alpha beta, depending on those channel coordinates, and I'm having the initial distorted wave K alpha, R alpha. And that is called the exact finite range amplitude, EFR, exact finite range DWBA amplitude. Exact finite range because I take into account all those changes of coordinates in the one and the other system, and you see what I have to evaluate is a 6-dimensional integral, which is not so easy. And therefore, after the 5 minutes break, we reduce that with a decent approximation to a usual 3-dimensional integral, at least for dp reactions. So see you then in 5 minutes.